Welcome to the deep dive. Today we're really getting into the weeds of AWS networking, specifically VPCs, virtual private clouds, and how you connect them up, both internally and, importantly, to your own stuff, your own infrastructure, that whole hybrid cloud picture.
Exactly. We've got this great guide, and it's packed with AWS features designed precisely for that kind of connectivity. It's quite dense, actually.
It is. So our mission today is to sort of slice through that density. We want to get the core concepts. What are these tools for? How do they actually work under the hood? And crucially, what are the key differences? Sort of a shortcut to grasping the essentials.
Yeah, and we'll try to make it visual, help you picture how these pieces fit together. Less jargon, more practical understanding.
Perfect. All right, let's kick things off with Network Address Translation, or NAT, and the two main players in AWS. NAT instances and NAT gateways. Now, the guide mentions why private subnets need NAT. Can you maybe paint a picture of that? Why can't they just, talk directly to the internet?
Okay, yeah. Imagine your private subnet is like a secure back office. You've got servers in there, maybe databases doing important work. They need to occasionally reach out to the internet, maybe for software updates, security patches, or calling external APIs.
Right, standard stuff.
But you definitely don't want to give each of those back office servers its own direct line, its own public IP address that anyone on the internet can just call up. That's a huge security risk.
Makes sense. Open door.
Exactly. So NAT acts like a central switchboard operator for that office. All the internal servers can make outgoing calls through this operator. When they do, the call appears to come from the switchboard's public number, not their private extension.
Ah, okay. So the outside world only sees the switchboard's number.
Precisely. The internal private addresses stay hidden. They get the outbound access they need, but without direct exposure. That's the core idea.
That switchboard analogy really helps. Okay, so one public face for many private resources needing outbound access. Let's tackle NAT instances first. What are the key things to visualize there?
All right, a NAT instance is basically an EC2 instance, a virtual server that you set up and manage. You launch it in a public subnet, one that does have a direct route out to the internet via an internet gateway. Think of it as setting up your own server in the front office.
Okay, a server I control in the public part.
Right. Then for the servers in your private back office subnets, you adjust their directions, their route tables. You tell them for any traffic heading to the internet, that's the 0.0.000 route, send it over to the network interface ID of that specific NAT instance in the front office.
So point all outbound traffic at that one instance.
Exactly. But here's a really crucial configuration step, something easy to miss. You have to tell that NAT instance server to stop checking if the traffic it's sending or receiving is actually meant for it. It's called disabling the source destination check.
Why disable that? Seems counterintuitive.
Because the NAT instance needs to forward traffic on behalf of those other private instances. If that check is enabled, it'll see traffic coming from a private instance's IP address and think, hey, that's not my IP, I should drop this. Disabling the check allows it to act as that switchboard, forwarding packets regardless of the ultimate source or destination IP within your VPC.
Got it. So it can actually relay the traffic.
Precisely.
Yeah.
And like any EC2 instance, you attach a security group to it to control what traffic is allowed in and out of the NAT instance itself. But, and this is important to visualize, you are fully responsible for this instance. Meaning patching the operating system, making sure it's sized correctly for the traffic load, and critically handling its availability if that single instance fails.
Your private instances lose their internet connection.
Exactly. So you often need to think about failover, maybe setting up multiple NAT instances with scripts to monitor and switch over if one goes down. It's a very hands-on approach.
Right. And performance just depends on the EC2 instance size I pick.
Yeah. Bigger instance, more bandwidth, more connections it can handle. Oh, and one more thing, because it's a regular EC2 instance you can access, you could potentially use it as a Bastion host too. A secure jump server to SSH into your private instances.
Interesting. Dual purpose, potentially. Okay, so NAT instance. Hands-on, flexible, but requires management and HA planning. How does a NAT gateway change that picture?
Okay, now picture this. Instead of you setting up that server, AWS provides a fully managed, purpose-built NAT service. That's the NAT gateway. You deploy it into a specific public subnet within an availability zone.
So AWS handles the underlying stuff.
Completely. They manage the infrastructure, the patching, the availability within that AZ. It's designed for high availability right out of the box within a specific AZ, and it scales automatically.
Scale how much?
It can handle bursts up to 45 gigabits per second, which is quite a lot of traffic. Way more than most single NAT instances could handle without careful sizing.
Wow, okay. That's significant. How does it get its public IP?
It requires an elastic IP address. You allocate an EIP and associate it with the NAT gateway when you create it. That gives it its static public face to the internet.
Always an elastic IP.
For connecting to the public internet, yes. There's a specific case for private NAT gateways, which connect to other VPCs or on-prem networks via transit gateway or a virtual private gateway. Those might not need an EIP, but for standard internet access, EIP is required.
And security groups, can I attach one like with the instance?
No, you can't directly associate a security group with the NAT gateway itself. Security for the instances using the NAT gateway is still handled by their own security groups, and you can use network ACLs on the subnet containing the NAT gateway for broader filtering if needed.
Okay. And for high availability across AZs, since it's HA within an AZ.
Right. Best practice is if you have private subnets needing internet access in multiple availability zones, you should deploy a separate NAT gateway in each of those AZs. Then configure the route tables for the private subnets in a specific AZ to point to the NAT gateway in that same AZ.
Keep the traffic local to the AZ. Why is that important?
Cost. If your instance in AZA sends traffic through a NAT gateway in AZB, you pay AWS data transfer charges for crossing that AZ boundary. Keeping traffic within the same AZ avoids those extra costs.
Good tip. Definitely something to watch out for. So NAT gateway sounds much more hands-off, scalable, managed.
That's the key difference, yeah.
So if we're comparing them side by side, what are the main trade-offs?
Okay, let's break it down. Availability. NAT gateway is highly available within its AZ automatically. NAT instance requires you to build your own HA solution.
Right.
Performance. NAT gateway scales up to 45 Gbps. NAT instance performance is tied directly to the EC2 instance type.
Management.
NAT gateway is fully managed by AWS. NAT instance requires you to manage the OS, patching, scaling, everything.
IP address.
NAT gateway needs an elastic IP for public access. NAT instance can use an elastic IP or a regular public IP, though EIP is recommended.
Security groups.
Attachable to NAT instance, not directly to NAT gateway.
SSH access Bastion.
Possible with NAT instance, impossible with NAT gateway.
And cost.
NAT gateway has an hourly charge plus a charge per GB of data processed. NAT instance cost is just the EC2 instance running cost, plus maybe the EIP cost if you use one, which is cheaper, depends heavily on your traffic patterns. Lots of data processing might make the NAT gateway more expensive.
Lots to consider there. It really depends on the specific needs, doesn't it? Control versus convenience, cost model.
Absolutely. But for most modern deployments needing scalable, reliable outbound access, the NAT gateway is generally the preferred, simpler solution, despite the data processing cost.
Okay, that clarifies NAT quite a bit. Let's shift gears slightly. Proxies, reverse proxies, Bastion hosts. The guide groups these together. Seems like they're all about managing access in different ways.
That's a good way to put it. They're all gatekeepers, but for different purposes. Let's start with a standard proxy server. What's its job?
Right. The guide says it's an intermediary, sits between users or maybe devices inside your network and the internet. It mentioned filtering, like based on website names.
Exactly. Think of it filtering outbound requests. You might use it to block access to certain sites or maybe enforce web security policies. It can also cache frequently accessed web content.
Cache! How does that help?
If multiple users request the same web page, the proxy can store a local copy after the first request. Subsequent requests for that page can be served directly from the proxy's cache, which is much faster and saves bandwidth. You typically deploy it in a public subnet, similar to where you might place a NAT instance.
Okay, so filtering and speeding up outbound web access for clients. Now, reverse proxies. The guide was a bit brief. It sits in front of web servers.
Correct. A reverse proxy does the opposite job. It sits in front of your servers, typically web servers, and intercepts incoming requests from clients on the internet.
So protecting my servers.
Partly protecting, but also improving performance and availability. Like a standard proxy, it can cache responses from your web servers. If someone requests a page that's already in the cache, the reverse proxy serves it directly without bothering your back-end web server. This reduces load on your servers and makes your website feel faster. You can also handle things like SSL termination and load balancing across multiple backend servers.
Ah, okay, so symbol distinction. Proxy manages outbound client requests. Reverse proxy manages inbound requests to servers.
You got it.
Now, Bastion hosts, also called jump servers. We touched on using a NAT instance for this, but what's the deal with a dedicated Bastion host?
Think of a Bastion host as a heavily fortified guard post. It's a dedicated EC2 instance, usually Linux or Windows, living in your public subnet. Its sole purpose is to be a secure entry point for administrators or developers who need to manage resources in your private subnets.
The only way in for management?
Ideally, yes. You don't expose your private database servers or application servers directly. Instead, authorized users connect only to the Bastion host SIMs, usually via SSH, port 22 for Linux, or RDP, port 3389 for Windows. From the Bastion, they can then jump to the private resources.
So it needs a stable address.
Absolutely. You assign an elastic IP so its address doesn't change, and security is paramount. You lock it down tightly. Network ACLs on the subnet and security groups on the instance itself should restrict access to only known, trusted IP addresses like your corporate office VPN range or specific admin IPs.
Very specific access control.
Extremely specific. You minimize its attack surface. You might even set up auto-scaling for the Bastion host for high availability, ensuring there's always a secure way in. But remember its purpose. Secure administrative access. It's not for general internet connectivity for your private instances. That's still the job of the NAT gateway or NAT instance.
Right. Strictly for management tasks. The guide mentioned port forwarding. How does that work with a Bastion?
Yeah, that's a common use case. Say a developer needs to connect their local database tool to a private database server. They can't connect directly. So they establish an SSH connection to the Bastion host and configure SSH port forwarding. This creates a secure tunnel through the Bastion. Their local tool connects to a port on their own machine, SSH encrypts that traffic, sends it through the Bastion, which then forwards it to the actual database server on its private IP and port. It's like a secure, encrypted pipe through the guardhouse.
Clever. Secure access without exposing the database directly. Okay, proxies and bastions make sense. Let's broaden the scope now, connecting entire VPCs. First up, VPC peering. What's the core concept visualized?
Okay, imagine each VPC is its own private island network. VPC peering builds a direct, secure bridge between two of these islands. Once peered, instances on Island A can talk directly to instances on Island B using their private IP addresses, just as if they were on the same local network.
Like extending the network across the bridge.
Exactly. And these islands can be in the same AWS account or different accounts. They can even be in different AWS regions and a region VPC peering. It uses the AWS backbone network, so it's reliable and performant.
That's useful. Any catches?
The big one. The IP address ranges the CIDR blocks of the two VPCs cannot overlap. If VPC A uses 10.0.0.016, VPC B cannot use any part of that range, like 10.0.1.024. They need completely distinct address spaces.
Okay, unique address space is required. What else?
Peering is strictly a one-to-one relationship. You can only have one peering connection between the same two VPCs. And a really important limitation is that peering is not transitive.
Not transitive. What does that mean practically?
Let's say you have three islands,
Yeah.
A, B, and C. You build a bridge between A and B. Then you build another bridge between B and C. Even though A can talk to B and B can talk to C, A cannot talk to C across island B just because of those connections.
So no automatic path through the middle VPC.
Correct. If you need A and C to communicate, you must build a separate, direct peering bridge between A and C.
Okay, every pair needs its own connection if they need to talk directly. What about connecting my own network, say via VPN or Direct Connect, to a peered VPC? Does that connection extend? The guide mentioned edge-to-edge routing isn't supported.
Right. Same principle as transitivity, really.
Yeah.
If your on-premises network has a VPN connection to island B, that connection stops at island B.
Oh.
It doesn't automatically grant your on-prem network access across the peering bridge to island A. You would need a separate VPN or direct connection directly from your on-prem network to island A if you needed that connectivity.
So peering is purely VPC to VTC communication. It doesn't act as a transit point for other networks.
Exactly. And you can see how this starts to get complicated if you have many VPCs. If you have, say, 5 VPCs that all need to talk to each other, you end up needing 10 separate peering connections. The formula is NN12. It becomes a mesh, complex matter.
A mesh of doom, sometimes called.
Yeah.
That sounds like it doesn't scale well conceptually, which leads us perfectly into Transit Gateway. How does this solve that scaling problem?
Transit Gateway is designed specifically to address the complexity of interconnecting many VPCs and on-premises networks. Imagine it as a central cloud router or a regional network hub.
A central hub instead of point to point.
Precisely. Instead of building bridges between every pair of islands, each island builds a single connection and attachment to this central transit gateway hub. Your on-premises network can also connect directly to the hub using VPN or Direct Connect attachments.
Okay, much simpler topology. One connection per network.
Right. It acts as a central point for routing traffic between all connected networks. It's a regional service, but it's highly available, spanning across all the availability zones within that region automatically.
So it handles the HA for the hub itself.
Yes. You attach your VPCs, your VPN connections, your direct connections, all to this one logical router. It supports IPv4 and IPv6, though the connected networks still need non-overlapping CIDR blocks.
That non-overlapping rule still applies then?
Still applies. And a really powerful feature for organizations with multiple AWS accounts is that you can share a transit gateway across accounts using AWS Resource Access Manager RAM.
So one central networking team can manage the hub and other account VPCs can just attach to it.
Exactly. Hugely simplifies multi-account network management.
What about connecting networks across different regions? Does Transit Gateway help there?
It does. You can establish inter-region transit gateway peering connections. So the transit gateway hub in, say, US East 1 can be peered with the transit gateway hub in U West 1. This allows traffic to flow between VPCs attached to either hub, effectively creating a global network managed through these central points. You just need a TGW in each region you want to connect.
Okay, so it scales regionally and globally. The guide also mentioned Connect attachments. What are those for? Sounds specialized.
They are. Think of a Connect attachment as a way to integrate third-party virtual network appliances like SD-WAN devices, next-generation firewalls, or intrusion detection systems directly with your transit gateway.
So routing traffic through my own security appliance before it goes elsewhere.
Exactly. It uses GRE, generic routing encapsulation tunnels, for efficient data transfer between the transit gateway and the appliance, and typically uses BGP, Border Gateway Protocol, to dynamically exchange routing information. This allows you to insert these specialized appliances into your traffic flow for advanced inspection, security, or WAN optimization managed centrally via the TGW.
Very flexible. So Transit Gateway really seems like the modern, scalable way to handle connectivity for more than just a couple of VPCs or for hybrid setups.
Definitely. It simplifies routing, centralizes management, and overcomes the scaling limitations of VPC peering significantly.
Okay, let's switch focus to accessing AWS services privately from within a VPC. This is where VPC endpoints come in, right? Avoiding the public internet.
Correct. VPC endpoints provide private connectivity from your VPC to supported AWS services without needing an internet gateway, NAT device, VPN connection, or direct connection. Traffic stays entirely within the AWS network.
Big security benefit there, and probably performance too.
Yes, enhanced security because traffic doesn't traverse the public internet, and often more reliable performance. It also simplifies networking, as you don't need to manage routes or firewall rules for public IPs for these services. But remember, endpoints are service-specific. You need an endpoint for S3, another for DynamoDB, another for EC2 API, etc.
Okay, one endpoint per service. Now, there are two main types mentioned, gateway endpoints and interface endpoints. Let's start with gateway endpoints.
Gateway endpoints are the slightly older style, and they're specifically available for only two services, Amazon S3 and DynamoDB.
Just those two?
Just those two for gateway type. They work by adding an entry to the route table of your subnet. You specify a prefix list for the service, AWS provides this, and target the gateway endpoint ID. When instances in that subnet try to reach the public DNS names of S3 or DynamoDB, the route table redirects that traffic to the private endpoint gateway instead.
So it's purely a routing change within the VPC.
Exactly. It's highly available within the region, and you typically create just one per VPC for each service, S3 or DynamoDB. A key limitation is you can't attach security groups directly to a gateway endpoint. You control access via endpoint policies and instance security groups.
Okay, route-based S3 and DynamoDB only. What about interface endpoints? They sound more versatile.
They are. Interface endpoints powered by AWS Private Link support a much wider range of AWS services, plus services hosted by other AWS customers or partners, VPC endpoint services. Instead of just being a route target, an interface endpoint provisions an elastic network interface, ENI, with a private IP address directly inside your specified subnet.
Like putting a network card for that service right into my VPC.
That's a great way to visualize it. It gets an IP from your subnet's CIDR range. Communication happens via DNS. When your instance resolves the standard DNS name for the service, like ec2.us endpoint ENI within your VPC, AWS DNS resolves it to the private IP address of the interface endpoint ENI within your VPC.
Ah, DNS magic redirects it internally.
Right. And because it's ENI, you can attach security groups directly to the interface endpoint to control exactly what traffic can reach it. For high availability, you typically create endpoint ENIs in multiple subnets across different availability zones.
More control with security groups, wider service support. Now, S3 is interesting because it supports both types. When would you pick a gateway versus an interface endpoint for S3?
Good question. For S3 access from within the same VPC, a gateway endpoint is often preferred because it's simpler and, crucially, it's free. There are no hourly charges or data processing fees.
Free is good.
Free is definitely good. However, gateway endpoints have some limitations, particularly with access from outside the VPC, like from your on-premises network over VPN or Direct Connect. Due to how they handle source IPs, accessing S3 via a gateway endpoint from on-prem often requires setting up a proxy server within the VPC.
Okay, so maybe not ideal for hybrid access.
Interface endpoints for S3 are generally better for hybrid scenarios. They provide a direct private IP, making connectivity from on-prem much more straightforward. They also allow easier cross-region access patterns. The downside is cost. Interface endpoints have an hourly charge per endpoint ENI per AZ, plus per GB data processing fees, though often cheaper than NAT gateway processing fees.
So cost versus flexibility and hybrid compatibility.
Pretty much. If you have heavy S3 or DynamoDB traffic purely within your VPC, using a gateway endpoint can save you significant money compared to routing that traffic through a NAT gateway, as you avoid the NAT data processing charges. But for broader access patterns or other services, interface endpoints are the way to go.
Makes sense. Okay, quickly now, IPv6. There's this specific egress-only internet gateway. What problem does it solve? IPv6 addresses are public, right?
Exactly. Since IPv6 addresses assigned to your instances are typically globally unique and reachable, you need a way to allow them to make outbound connections to the IPv6 internet, for example, updates, without allowing the entire IPv6 internet to initiate connections inbound to them.
Like a one-way door for IPv6.
Precisely. The egress-only internet gateway is stateful. It lets instances initiate outbound IPv6 connections and allows the return traffic for those connections back in. But it blocks any new inbound connection attempts from the internet to those instances over IPv6. It's similar in concept to NAT for IPv4's outbound-only benefit, but specifically designed for the public nature of IPv6. And like NAT gateways, no security groups attach directly to it.
Got it. Securing IPv6 outbound access. Now, VPC Flow Logs, you described these as network security cameras earlier.
Yeah, that's a good analogy. Right. VPC Flow Logs capture metadata about the IP traffic going to and from network interfaces within your VPC. It doesn't capture the packet content, just the information about the connection.
What kind of information?
Things like source IP address and port, destination IP address and port, the protocol number, TCP, UDP, ICMP, etc., the number of packets and bytes, the start and end time, and crucially, whether the traffic was accepted or rejected based on security group or network ACL rules.
Accepted or rejected, that seems really useful for troubleshooting.
Incredibly useful. You can enable flow logs at different levels for the entire VPC, for specific subnets, or even for individual elastic network interfaces, ENIs. You choose where to send the logs, either CloudWatch logs for near real-time analysis and alerting, or directly to an S3 bucket for longer-term storage and batch analysis.
So it gives you detailed visibility into what's actually flowing or trying to flow across your network interfaces.
Exactly. Essential for network monitoring, troubleshooting connectivity issues, why can't my web server talk to my database, security analysis, spotting unusual traffic patterns, and meeting compliance requirements.
Okay, great tool for network visibility. Now let's talk about stretching the VPC geographically. AWS Local Zones. What's the picture here?
Imagine AWS setting up mini extensions of their main regions, but placing them physically closer to major cities and population centers. That's a local zone.
Bringing AWS compute closer to users.
Exactly. They have their own direct internet connections and often low latency links back to the parent AWS region. You can launch certain AWS services directly within these local zones, primarily EC2 instances, EBS volumes, some RDS database types, S3.
Why would you do that?
The key benefit is ultra-low latency. For applications where a single-digit millisecond latency to end users in that metro area is critical, think real-time gaming, live video streaming, virtual workstations deploying resources in a local zone can make a huge difference compared to running them in the main, potentially distant AWS region.
So reducing the physical distance for latency-sensitive apps.
Precisely. They're fully managed by AWS, just like the main regions, but located in these specific metro areas, and integration is seamless. You extend your existing VPC into the local zone by creating subnets there. You use the same route tables, security groups, and NACLs to manage resources in the local zone as you do in the main region.
Okay, so physically closer compute for low latency. How does AWS Wavelength then fit in? It sounds even closer and involves a carrier gateway.
Wavelength takes that closer to the user idea to the absolute edge. It embeds AWS compute and storage infrastructure directly inside the data centers of telecommunications carriers, right at the edge of their 5G networks.
Inside the phone company's building?
Essentially, yes. A wavelength zone is an AWS deployment within a carrier's facility. The goal is to provide ultra-low latency access for applications running on mobile devices connected to that carrier's 5G network.
Okay, extreme low latency for mobile. What's the carrier gateway's role?
The carrier gateway is the connection point between your VPC, specifically the subnets you create in the wavelength zone, and the carrier's mobile network, 4G, 5G. It primarily allows outbound traffic from your EC2 instances in the wavelength zone to devices on the carrier network. Direct inbound traffic from the internet isn't typically supported. It's focused on serving content or processing data for mobile clients. It also acts as the default gateway for those subnets and handles network address translation for the instances within the wavelength zone.
So it connects my wavelength instances to the mobile users. What services run there?
It's a subset, focused on edge compute, EC2, EBS, container services like ECS and EKS, plus supporting services like CloudWatch, CloudTrail, Systems Manager.
And the prime use cases.
Things needing the absolute minimum latency to mobile devices. Think connected vehicles, real-time inference for mobile AR/VR, interactive live video streaming, cloud gaming delivered directly over 5G.
So local zones for metro low latency, wavelength for ultra low latency right at the 5G edge. Got it. Okay, last major section. Connecting our VPCs back home to our own data centers. Hybrid cloud networking. Let's start with AWS Managed VPN.
Okay, AWS Site-to-Site VPN provides a secure, encrypted connection between your on-premises network, your data center or office, and your AWS VPC. This connection runs over the public internet.
Secure tunnel over the internet.
Exactly. It uses the industry-standard IPsec protocol to create encrypted tunnels. On the AWS side, you have a virtual private gateway, VGW, attached to your VPC, or you connect to a transit gateway. On your side, you have a customer gateway device, a router, or firewall. AWS provides redundant tunnels to different endpoints for high availability.
What about performance? It's the internet, right?
Because it relies on the public internet, performance and latency can be variable. It depends on your internet connection and general internet congestion. It's generally suitable for moderate bandwidth needs or as a backup connection. Pricing involves an hourly charge per VPN connection, plus standard AWS data transfer out costs.
Okay, secure, relatively easy to set up, but variable performance. How does AWS Direct Connect contrast with that? Sounds more substantial.
It is. Direct Connect, or DX, is a dedicated private network connection between your premises and AWS. Think of it as leasing a private fiber optic circuit directly into an AWS Direct Connect location.
Bypassing the public internet entirely.
Completely. This provides significant benefits. Much more consistent network performance, lower and predictable latency, and dedicated bandwidth options, typically from 50 MLBPs up to 100 GBPs.
Wow, big difference. Any downsides?
It's a more complex and generally more expensive setup process. You need to work with an AWS Direct Connect partner or have equipment and a colocation facility that houses a DX location. And, importantly, the raw Direct Connect link itself is private, but not inherently encrypted.
Non-encrypted, so my data is in the clear.
Over that private physical link, yes. If you need encryption for compliance or security policy reasons, you typically layer encryption on top, often by running an IPsec VPN over the Direct Connect circuit. Direct Connect uses virtual interfaces, VIFs, to segment traffic. Private VIFs connect to your VPCs via a VGW or Direct Connect gateway, while public VIFs allow private access to public AWS services, like S3 or EC2 APIs, using public IPs but staying off the internet. It relies on BGP for dynamic routing exchange. And you can bundle multiple physical connections into a link aggregation group, LAG, for higher bandwidth and redundancy.
Okay, DX. Dedicated, high performance, consistent, but more setup effort, and needs encryption added if required. What's the AWS Direct Connect gateway then? Sounds like it helps manage DX connections.
Exactly. If you have multiple VPCs, potentially across different AWS regions, that all need to connect back to your on-premises network via Direct Connect, Managing separate private VIS for each VPC can become complex. The Direct Connect Gateway, DXGW, acts as a central hub for your Direct Connect connections.
A hub for DX, like Transit Gateway, is a hub for VPCs.
Sort of, yes.
Yeah.
It's a global resource. You connect your Direct Connect connection, specifically a private VIF or a transit VIF, to the Direct Connect Gateway once. Then you can associate that single DXGW with multiple virtual private gateways, VGWs attached to VPCs, or, more commonly now, with transit gateways, TGWs, across different regions.
So one DX connection can reach many VPCs globally through the DXGW.
Correct. It greatly simplifies hybrid connectivity at scale. If you're using transit gateways to interconnect your VPCs, you typically connect your direct connection to the DXGW using a transit VIF and then associate the DXGW with your transit gateways. AWS recommends redundant direct connections terminating at different DX locations, each with a transit VIF to the DXGW for proper high availability. Just be mindful of account limits on TGWs, DX connections, and DXGW associations as you scale.
So DXGW plus TGW seems like the powerhouse combo for complex, multi-region hybrid networks needing high performance.
That's definitely the modern best practice for scalable and resilient hybrid connectivity using Direct Connect.
Wow, okay. We've covered a huge amount of ground. From basic NAT for internet access, managing entry points with proxies and bastions, connecting VPCs with peering and the more scalable transit gateway, accessing services privately with VPC endpoints, handling IPv6 securely, monitoring with flow logs, pushing compute closer with local zones and wavelength, and finally linking back to on-prem with VPN and the powerful direct connect options. It's a lot, but hopefully seeing how they fit together helps. Each piece solves a specific problem. And understanding those problems, security, scalability, cost, performance, latency, helps you choose the right tools to build the network architecture you need.
Absolutely. You should now have a much clearer mental map of these core AWS networking building blocks and how they interact.
Yeah, the foundation is there to start designing effective solutions.
You know, thinking about all this, especially local zones and wavelength, it really makes you wonder about the future. With applications demanding ever lower latency and hybrid setups becoming more common, how will these lines between cloud, edge, and on-premises continue to blur? What kind of new networking innovations might we see next? And how will that change the way we even think about building and experiencing applications?
That's a fascinating thought. The pace of innovation in cloud networking is relentless, driven by exactly those application needs. It will be interesting to see what comes next.
It certainly will. Thank you for joining us today.